Good evening and welcome to this evening's webinar, IB with TI Nspire Calculus, hosted by Texas Instruments Australia. My name is Rodney Anderson. I'll be your host for the webinar. The webinar is being recorded and will be available to view at a later date along with the panelist documents. It is recommended that you view the webinar and not try the activities as you watch live, as you can pause, fast forward or rewind the recorded webinar at a later date. Now, during the webinar, so if you've got any questions or like to chat to the hosts, myself, Rodney Anderson, you may wish to actually move your cursor up to the middle of the screen. You'll see a pop-down menu and you can click on chat. And if you have a question, please direct them to me, the host, via the chat space. Also, during the webinar, you may wish to use your phone to listen to the audio. So you should see the toll-free number, and there is the meeting number, and you'll actually have to press hash there as well. Follow the instructions on the screen. So at the conclusion of the webinar, feedback is very important to the panelists and Texas Instruments Australia, so please take the time to respond to the survey and we can improve on the excellent webinar series that Texas Instruments Australia has. In 2 days you'll get an email delivered to you and there'll be links and resources to links and so forth, and there's also a link to your webinar certificate, which is great for professional development hours. Our panelists, Bozenna Graham, as you've heard before, a wonderful presenter, a T-Cube national instructor, a very, very experienced teacher with the IB program. And our first panelist for the night is Pam Durrant, and she's at Wesley College as well. Welcome, Pam. Welcome, Bozenna.
Thank you, Rodney.
Pam asked her to start off her session for tonight's webinar. So over to you, Pam.
Thanks very much, Rodney. So what I'm going to look at tonight is some little activities that you might like to do at the start of differential calculus when you're presenting it to your class. So generally speaking, with differential calculus, I always start with the difference between an average rate of change and an instantaneous rate of change, so looking at a graph and looking at the secant and the tangent. So I'm going to look at this in a couple of ways on the TI Nspire. The first way I'm going to do it is through a calculate page, and then I'll also do it through the graph page. And depending on the type of students you have, whether they're visual learners or not, one of these might be quite appealing to you to try. So I'm going to define a function, so I'm opening up a calculate page here, and I can define a function through menu actions define. These sorts of things are always much easier to do on your computer software and to display that, and the students are actually able to now get student software packages, which makes it easier for them to work on a laptop as well as doing the handheld. So I'm just going to define a function, f of x, and I'm going to make this one 3x squared minus 2x plus 1. So once I've got that, it tells me that that's been done, so that's good. And now I'm going to do an average rate of change. So I'm going to set up a fraction, and I'm going to do the average rate of change between 1 and 3. So as you would on the board in your classroom, you can enter that in, and it tells me that the average rate of change is 10. Now, just because it's the non-CAS calculator doesn't mean that you can't set up things in a similar way as you would on a CAS calculator. So now what I'm going to do is do the same process but make it a little bit more general. So defining it over B minus A there. And I'm then going to do the given, which the given symbol is on the equals menu, and it's this vertical line. So if I put in A equals 1, and you do need a space between the 1, the and the B equals 3, I get that same result. Now the good thing about defining a function and then using it in the general form on your screen is you can then use the up arrow, grab what you've done there and quickly alter the value. And if the value that you're altering is the second one entered, it makes life a lot easier, so you don't have to edit too much. So I can do that a few times, just going up and enter, and I might do it at 2, then think, well, we're actually going to get a little bit closer. Oops, went too far, sorry. If I now go to something like 1.5, and you can see that gradient is decreasing as we go, and if I then start going to like 1.1, 1.01, and we can see that it looks like it's limiting, and so you can bring in the idea of a limit to your students that we're getting closer and closer to 4 but never quite getting there. So of course when I teach gradients and secants and tangents, the next thing is to actually have a look at what happens at the derivative, so at the tangent there. So I'm going to get the numerical derivative at a point, and I'll use x. So my value is at 1 in this case, and it sets up the template beautifully for me. I just put in my defined function, and it tells me that the value is 4. So if we then open up a graph page, we can use that same defined function, because anything that is in the problem number 1 series will always be connected, and this is the great thing about the Nspire calculators, is how the pages are connected from one to the other. So I'm going to now go into a graph page and use that same function and show you how you can determine the gradient, and then we're going to look at how we can create that whole secant. So here I just need to put in f of x, and you'll notice that it's bolded here because it has been defined on a previous page, and there it is there. So using the menu in the graph settings with the analyze graph, there's a whole lot of things that we can analyze on that graph, but I'm interested in the gradient at the moment, so I'll take that gradient, and I can position my cursor and it will tell me the gradient at various points. But if I want to choose a particular value, then I just need to enter that value. So if I type in 1 and enter, it tells me the gradient is 4. So we can see that that matches up with what we had here on the calculate page. Okay, so the other thing that we can do is now actually look at drawing a, well, the secant can be drawn, but it can't be measured very well. So I'm actually going to draw a line through 2 points. So I'm going to use the geometry menu. As I said, this would be good as an introductory activity because the geometry setting is not switched on in the press to test mode, so not good for examinations. So at this point I'm going to put a couple of points on my graph. So I'm using the geometry setting, points and lines, point on, and I'm just going to mark them anywhere. There's one, and I'm going to do another one. So click it there, and I'm going to press escape, and now what I'm going to do, now that I'm not in the geometry setting, is I'm going to edit that, and you can do that by double clicking. Once again, this is really easy in the computer software in particular. So I'm going to enter that as 1, and you can see the point is immediately 1, 2. I'll just put that over there. Go up here, and if I put in that original point 3, and it tells me there's the point there, I'll just move that off slightly. Okay, going back to the geometry menu, I'm now going to do a point and line, and I'm going to do a line, and I'm going to go through those 2 points. So if you just click carefully, it creates the line. Press escape again, and this time I'm going to measure the slope of that line, and you can see there that the slope is 10. Now once we've got that, in the geometry, in the graph page, it's really nice then to actually grab this point and see what happens as we move. And what we can see happening is as the point is changing, so too is the gradient, and we can bring that down really nicely, and we can see that change in the slope where it was 10 to now coming down 5.7, etc. And depending on how skillful you are, you can almost get that point right on. I can never quite get there, but you get the idea that they get that limiting idea of the gradient there. Okay. So one of the other things that you can do with the calculator is find the gradients of a tangent. And so there was a really nice portfolio task a few years back, some of you might remember from high level, called the zeros of cubics task. Basically you just needed to define a cubic on a graph page, find the x-intercepts, go to the midpoint of two of those x-intercepts and determine the equation of the tangent and see where that tangent intersects. So I'm going to put a cubic in. So I've got a graph page here, and the lovely thing about 4.2 operating system is we no longer need to put multiply signs in between our brackets as we type them in. So here's a cubic, and I press enter, and I can see that nicely there. So as you can see from the equation of the cubic, we can immediately recognise that those intercepts are at 1, -2 and -1. So we can find the midpoint of any of those three, but the easiest midpoint will be to use at x equals 0. So I'll just put in f1 of x. Now notice I'm in a different problem number now, so this is no longer connected to that first part with the average rate of change graph. So I put that in, and I'm going to determine the equation of the tangent at x equals 0. So first of all, I'm going to analyse the graph, go to dy dx, and I'm just going to type in 0. So that's as I did before, and it tells me the gradient is -1. So then I can find the equation of this tangent. So menu, geometry, points and lines, tangent. Now this will draw it anywhere, but I specifically wanted at that point. So the good thing about finding that gradient earlier was it allowed me to have a point on the line that I can click straight to. Whenever you're in the geometry menu, you'll see that little symbol up there, and if you want to do anything with your tangent line, then it's best to escape first. And then what I can do is move that around and I can have a look, so I'll just quickly do that so you can have a look and see how the gradient changes, what happens to the tangent, etc. But we'll try and get back there. Just missed it. Sorry. I might just quickly do that again. Sorry. There's 0. There it is. I think I've just clicked on the same point.
You can always just delete your equation there and just
Yes,
control
I think I will. There we go. Delete. There we are. And sorry, I'll only be a moment. That was a bit of a diversion. Not quite getting the point.
That's okay. You like doing that way as you're doing that. There, you got it.
There we go. Okay, so what we actually want to do is get that equation of the line, and we want to now see where that intersects. So I'm going to use the graph entry, and now I can use this relation, or I can use the function. I'm going to stick with the old function way, but you can now in 4.2 use the relations. So I'm just going to enter that, and we can see immediately that it looks like there's a point of intersection there, and it looks like it's at our other x-intercept, and we can of course analyse that with the intersection and go between, oops, I just better escape there. And go between, and I've just managed to wiggle my line a little bit, so it hasn't quite gone through, but sorry about that. I'll just go back and delete that. Managed to rotate my line just a touch, so yeah, I'll put that back in. Okay, hopefully this time I'll get it. And there we have the other point of intersection is exactly our other x-intercept. So it's a really nice proof, in particular for the high-level students, that that always does come true. But then, of course, it could lead as a possible exploration investigation as to whether that works with complex solution and whether it also works for higher order polynomials like quartics or quintics, etc. All right, so moving on. When you define a function through a graph page, it's also connected to the calculate page. And what I want to look at now is the gradient graphs and the graphs of the second derivative and the connection. So I've got a quartic here, and I'm just using the factorised form because it makes life easier for putting that in. So I'll just quickly put that in. 2 minus x. Once again, we don't need those multiply signs, which actually is much quicker for when you are doing the work on the computer. So I've got that in there. I'll just move my label out of the way. And what we can see now is we can use this graph, and I deliberately chose a quartic so that we can see a bit of a difference in the derivatives, etc. So if we then go to F2 of x, so I can use the template, I like to call this my favourites menu, over here, and use the derivative. And if I type in F1 of x, so the previously defined graph, here it is here. And I can zoom out a little bit so I can have a look. I will just so we can see a bit more of it. And once we've got that, I can also do another graph entry, and this time I can put in the second derivative, which is next to it there. So with respect to x, and once again f1 of x. Now just a point of note, you can't actually do the derivative of the derivative. That doesn't seem to work, but you can certainly get the second derivative there. Once you've got all three, I might just hide that label. Oh, no, I've hidden the wrong thing. Get rid of that, sorry.
You can always go Control Escape, you Control Z.
Yes.
See how you go.
I will just go Control Z.
There you go.
There we go. Yes. Once we've got that, we can then use the trace. So the trace menu is really nice for getting around the graph. So it's starting on f1 of x there, and it generally will always jump to a y-intercept of the first graph defined. So I can move across, and as I move across, you can see the values changing, and nicely it tells you, I'll just go back there, when you hit a 0, so when you hit an x-intercept, it also tells you the exact coordinates of a maximum. But the beautiful thing about doing this is then jumping between the graphs. So I'm at a maximum now on my original graph, and if I hit the down button, it takes me then to one of the other graphs. In this case, it's jumped to F3. So if I go up or down. So F2, so I just go back, so the maximum there, if I go up to F2, it tells me it's a 0. And if I go up again, you can see that the value on the second derivative is a negative, so it makes that connection that the second derivative will have a negative value for a local maximum. And likewise, I'm now back on the original graph, so I can go back and find the local minimum there, which is at the 0. And once again, if I go up, I can see that the first derivative has a value of 0 and the second derivative has a positive value, giving me that local minimum. Going back to the the first derivative, if I move around that and get to its minimum down here, and then go to the third derivative, the second derivative, F3, I can see that the minimum on the derivative gives me a 0 on the second derivative, and if I go back to the original graph, you can see that that's actually the point of inflection, the non-stationary point of inflection, so where we get that change in concavity. So that's quite a nice thing, and you can do that with lots of different graphs. Okay, skipping through, that was that. So you can certainly have lots of discussions with your class then about what the connections are. So it's going through using that graph trace and then moving left and right to stay on a particular curve and using the up and down arrows to get between the different functions. And on a graph page, it is actually very easy to determine the values of the maximum and minimum values, but you can also do that on a calculate page, and there is a function within the calculus menu that perhaps isn't used very often, and that's the numerical function minimum or maximum. I'm just going to use the maximum today because on that particular graph there were two maximums, so that's quite a nice thing to do. So if I type in that original function that I've defined, that quartic, you must always, when you're using one of these actions for it to find the function maximum, that you must do it with respect to a particular variable. So I do that and I get the value of 1.5811. Now that is an X value of where the maximum occurs. So it's not the maximum value of the graph, it's where the maximum value occurs. But when we saw that graph, we did see that there were actually two solutions. So in order to find the second one, you'll need to enter a domain restriction. So the menu, calculus, n function maximum, f1 of x, comma x, and then a domain restriction. So we use that given symbol again. And generally, when it's trying to find solutions, it will always try and find the first solution greater than 0. So let's put in x being less than 0. And we get the second solution. To get the y values of those, you simply need to do f1 of x. Well, there are two ways you can do it. This is one way, f1 of x at, and you can take that value and put it there. Oops, sorry, need to put x equals. Let me just go and slip that in. And it will tell me the actual maximum value of the function. So I can do it that way. I can also go f1 and just grab that value and put it in, and it will also give me the same result. Okay, the last thing I want to have a look at is the things that you can do when you get a table of values generated with a graph. So I'm going to use e to the x because that's a nice one for introduction into later calculus things. So the E button is located either directly here on the left-hand panel or through the pi button. There is also another E. Don't use the alphabet, that doesn't work. So if I enter that, And then if I go to table, and I can split screen my table, and so I can see the values here of all of the e to the x, and generally speaking it'll start close to 0. At the same time, oops, if I get back into the graph menu, at the same time if I put in the derivative function of f1 of x, what I then get, let me just remove the table. Okay, so let me just put that there. So immediately you can see to the students that, well, we're looking at the same graph, it appears, but if we put that table in, we can see that the values are identical as we go through. Then it's just a matter of editing that first function, so going up through where you were, and if I put in the log function, I can see my table of values. Now perhaps it's not quite so obvious to the kids that, you know, this is 1 divided by x, but with a bit of help along the way, hopefully they'll see that. And of course for high level students, you can of course put in log of absolute value of x and have a look at the difference there. Okay, very last thing, I hope I'm not taking up too much time. If I put in sine of x and also cosine of x here, so I can have a look and see that those are there. What we can do back on a calculate page once those are defined, so just taking a note, that's F3 and F4 of x, I can then do some calculus with those, and you can have a look at some nice things like, oops, F3 of x multiplied by F4 of x, sorry, forgot I wasn't using CAS there, sorry. I of course need to do it at a point, so I can put in x equals, and if I put in angle, I'm in radian mode, so I'm going to put in pi on 6. The pi button is located here, but nicely pi is pretty much there, so I can type pi and the calculator is extremely clever and knows that that's what I mean. So you can do some nice things here if I were to just put a 2 in there, so I can then compare it with, if I put in this, of sine 2x at pi on 6, and just because we can, it is in radian mode, but when we do have an angle given to us in degrees, we can still use the degree mode so long as you actually enter it in degrees, and it will know to convert it to radians because that's the mode that the calculator is in. So you can have a look and see that, well, 2 lots of sine x cos x gives us the same result as sine 2x. Why is that? Going through our double angle formulae. And of course you could also do the quotient of sine x over cos x. So that was f3 of x over f4 of x. Oh, sorry, once again, forgot to put my value in. And if I just put in something that they perhaps don't know, pi on 8, so we can get those sorts of values for tan x, etc. Okay, well, I think that's about everything I've got to show you, and I hope that you have some enjoyment with the TI Nspire calculator introducing differential calculus to your classes, and I'll now pass over to Bozenna.
Thank you, Pam.
Thank you very
Great
much,
introduction.
Pam. It was excellent, really nice tricks and lots we could learn from this presentation. So I will share my screen now. So as we could see, Pam looked at average instantaneous rates of change, this nice zero of cubics activity, and using numerical function max and min, which is not very common, but it works very nice, and also looking at trays and graphs and tables. What I've prepared for today are the activities, which the first one is looking at modeling rates of change, then one of the optimization problems with data capture. I also find a noise derivative analysis demos. I will show this one, and I will look at continuous probability distribution. And also in 4.2, it's very easy to press to enter, press to test and exit using the navigator. And I might also look at some new features in 4.2 and what is possible if we still have some time. So I will start with instantaneous rate of change and motion of the door with an automatic closer. So the idea is that we can have a door, and that was the diagram, and we, at time 0, someone pushes the door, opens it, slows down, and then the automatic closer starts closing the door, and it gets shut after 7 seconds. And what we'll try to model here is the number of degrees, which we'll call d as the function of time. So the first task for the students would be to try to sketch a reasonable graph of d versus t. So of course we might talk to the class, do you expect the graph to be symmetrical, which would be faster door opening or closing, how much would the door open, and so on. So they could sketch it by hand, but of course we could also use the scatter plot, where they would need to enter 2 lists. I did the first symmetrical, so I have those times a bit, and then I looked at degrees. We can also ask whether the door would actually open 95 degrees or 100, and a nice discussion. If you have a door like that at school and a stopwatch, they could even do some track experiment to get the data and see how it works. The other way to do is use the spreadsheet, of course, which is a bit easier because you have matching pairs. So the students can think what would happen and then put their values and create the graph. And of course, they could move some values thinking whether this should be faster here, so they could move the point and so on. So that's the first approach, which actually gives them some idea whether it is the faster rate of change and then slowing down, and you can move only 1 point at a time. So from here we would go that suppose that the function, the number of degrees as the function of time, is given by this formula, 200t times 2 to the power negative t. And we'll ask the students to plot this graph and see again what happens. So as we can now discuss, there is a much faster rate of change, positive rate of change when the door opens, and then because of this automatic door closer, it will be closing slower. And then we look at positive, negative, stopping on the top, and that's something the students, I believe, could feel actually what happens. So now we can also make a table of values looking for each second from 0 to 10. So as Pam showed, Control T or using menu, we can get the table of values. So the students can actually go up and down. So starting at 0, after 1 second goes to 100, and then after 10 seconds we see it's down. Of course, you could change the setting, or if we are in the calculator, in the graph screen, we can use trace. And if we go graph trace, so you could either use the value or you could say 1 and it gives us the value at 1. We can put 0.8 and it gives the value. So it's either moving with the arrows or entering the values. It's another way of doing that and having a discussion how quickly the door is opening, and then if we move to the other side, what is happening on the other side when it is closing, and we can watch the rate of change just physically by looking at the values only. After that, we would ask the question at time t1 second, does the door appear to be opening or closing, and how do you tell? And then, of course, we could have a discussion with the students. What I did here, as Pam showed before, I entered the equation of the tangent and make it at 1. So that's the equation, but it is the value of the gradient, which can also be done in the calculator screen using the derivative at a point. So clearly, it's a nice discussion what's happening, and later we can, of course, drag this point and see how we can look at the rate of change at different values of time. And at any time, you could, again, go there and retype your value. So that's something the students can play with. So we could also look at the average rate of change with at which the door is moving in this time interval. And again, looking at the gradient of the second, and we get 26.3, which is positive, so that gives us this idea of the door still opening, the angle increasing. And then we can find the estimate of the instantaneous rate of change. So what we can do, we can use a spreadsheet. So I call the first column T1 and the other gradient. And of course, if we decrease the time difference using the gradient formula, we can see what happens. It doesn't show those values, but they are actually small, so it doesn't display. And we can see that we are again getting the limiting value, but this time we arriving at the limiting value using the spreadsheet. We could use a symmetric difference quotient. So if we want it at 1, we go from 1.001 to, like, from this point to this one. So I did that in the notes page. Enter. So we get this value, and then if I enter here, I get a negative value. So we can see that around 1 it's positive, but if we move to 2 seconds, it is a negative rate of change, looking at the estimate by getting, again, this gradient. So now we would like to see in what way the values of the first derivative at 1 and 2 correspond to the graph, and how can we tell, what can we tell about the motion of the door by looking at those gradients. So we can again answer this question by sketching the graph of the derivative, and as Pam showed, we can match those values using the trace graph and graph trace, and again moving between maximum and minimum. So that is another application of the skills which Pam showed how to do. If we get to maximum, and then if I go down, I will get a 0. So again, combining those concepts, maximum on the graph of d next and 0 on the first derivative at the same point. Of course, we could simply use the maximum and minimum values and join those points again. That is looking at the point of inflection, again connecting the the first derivative minimum with the original graph. And the question would be, what would we expect the second derivative at this particular point to be equal and confirm that graphically and numerically. So we're sketching the second derivative graph, and of course those 3 points are lined up and matching. And the last question here would be what name is given to this point, and we could also use numerical solve for the second derivative solve for 0 to get the x-coordinate of the point of inflection. So that is the first of the activities. The second activity I would like to look at, I just move it to the start, is the optimization problem. Well, I will look at how can we actually solve the optimization problem. We want to inscribe a cylinder in a cone. So the cone has a radius of 4 centimeters and the height of 12 centimeters, and we will try to get the maximum volume of the cylinder. So the initial approach, I made a construction where students can calculate the volumes of cylinders with radius equal to those particular values. So basically by moving this point, I can observe how the volume changes. So if I go 86, 89, and then it drops down. So it is measuring the radius and the height and calculating the volume using this formula, but it is a nice activity for the students to basically be doing it themselves and see what happens. So you might have a very skinny cylinder or a very low-height cylinder and see how the volume changes. The next thing, we can capture what is actually happening here. I have already done it there, but I have a file here which is cylinder in a cone for students. And how do we do that? So I still have my graph there. And if I want to, you can have that prepared as I did, but because I already moved a few things, I have those things done. But if we start with this graph, and now I will put a new spreadsheet, I will call that I already used that, so I call it radius 1, and I call it volume 1. And what I'll try to do here, I will try to capture, data capture, and I will do it automatic. And if I go to variables, I will capture radius here. And for this one, if I go to menu, data capture, again automatic, but this time I want to capture the volume. And I already have 1 point, and now if I go back to my graph and I start moving this point, so it captures all those values and it creates the graph for the students to see. So that is the graph, or if you want to put a new graph, I called it radius 1 to create a new graph and volume 1. So we clearly see that that's the graph, and if you go back you can get more points. What we can do, we could do the cubic regression here, because later we'll of course show that it will be a cubic function, and it gives us those numerical values, which is cubic, any significant numbers here, which is x cubed and x squared, and then this can be related to the calculus calculations later. So if I go to my problem there and back, so now we want actually to use calculus. So write the volume of a cylinder in terms of radius only. So there is a hint here you might find useful to determine the equation of the straight line first, and you would do that in class, and of course that is the formula, pi x squared 12 minus 3x. And if you actually get them to calculate 12 pi and 3 pi, you can refer to the values which they had here, which are actually minus that and that, which matches. So then they would know that they actually got the right answer here. So that is the graph by using calculus and getting the maximum volume, which is 89.4. They could have estimated this volume, that's one of the questions here, by going what is the maximum. As we can see, it is about 89 point something. And then using calculus, of course, we confirm it is 89.4 at 2.67. And we could use numerical solve as well and get the x value and then the y value at this particular point. How can you show using calculus that it is a maximum value? Again, we can use the table of values, and we know that we are 2.68, so we go to the left, which is positive, and we go to the right, which is negative. Therefore, at this point, so that is using the table of values. Even in the exam, they can get those numerical values showing that something, the gradient changes, so that's why it is a maximum. So that was the second activity. Now, I found this file which on TI Nspire, and this is a really nice file showing positive, negative gradients. So if we move this file, it actually shows slope positive, slope negative. So that is something they can do with various functions. And that would be probably introduction to differential calculus, and also it can be done by using slope is positive here and then going down slope is negative. This is one of the functions, but you can change the entry, Control G, and put another function. It will still work. And now the second bit here is looking at the concavity of the graph. So again, if we drag point X, so we can see concave up and then concave down, and we similarly have a slider here where we can say, if I go here, this part of the graph is concave up, this part of the graph is concave down, and then we have stationary, non-stationary points of inflection when it joins. So that is a nice file just to play for the students, looking at positive, negative slope and concavity. And if you do Control G here, you could actually change the original function and it will still work with whatever function we have. The last activity which I prepared is looking at continuous distribution probability density functions using the piecewise function. So that's basically only in high level. The other activities can be used across study standard level and high level, adjusting, of course, to what we need to do. So we look at the piecewise function being probability density function when we have a pronumeral in the second interval. We want to find the value of A, sketch the graph, justify that this function for the given value of A is a valid probability density function, calculate those two probabilities, and then state the mode, mean, and median should be here, sorry. So if we start by looking at the integral from 0 to -1, we know it's 0.63. What I did here, I changed that to approximate to fraction, which is in number, which is 2/3, so we need to go 1 minus 2/3 is 1/3, so we know that the area of the triangle is 1/3. I made this construction here, so this is the parabolic part and the straight line part. So we know it's 1, 0, A, 0, so clearly the area of the triangle is A minus 1 times 1 on 2. If we do numerical solve for A, area of triangle needs to be 1/3, that's what we had left, and we change to a fraction, we get the value of A being 5 on 3. And then if we sketch this graph with the given value of A and calculate the area, which the big advantage here is that if it is a piecewise function, you can simply find the bounded area or just integral under the curve. It will give you the value of 1. So because the PDF is non-negative and the area under the graph is 1, we clearly have a valid PDF function here. This is not the best example as x and y are equal and students usually mix up those values, but they need to know that the mode is the x value for which we have a maximum. So in this case, it will be equal to 1. Then to calculate those two probabilities, since our function is defined, you just need to use definite integral 0 to 3/2 and 2/3 to 5 on 3 to find the required probabilities. Now, if we want to find the median, we, of course, the calculator will not solve with m as the upper limit because it's a non-case, so they will have to do it by hand to arrive at this cubic equation, and then they would need to use polyroots, which gives us 3 solutions. We could restrict the domain here. For given domain, we would only get this one, but clearly we can see median can only be 0.832 as the other values are not in the domain defined for this function, and the mean is x, f1 in x. So that was this activity. Now, what I would like to show now is what we have in 4.2. If I look at, I actually had my class open here. If we go to tools, and you see in tools, that's a navigator, but that would be as well in the teacher software. If you go to tools, you can see prepare handhelds. And if I go enter press to test, you can actually do the selection for the students. So with year 11s at the start, they really never know which ones to tick and tick, and there is lots of difficulties. So if you have the configuration here like IB exams, we limit geometry, disable vector, those ones, 3D graphing implicit, but the rest stays. And then if I now have my class connected wirelessly with the heads, and I say enter press to test, it goes to all kids' calculators and they are set in this mode. And once they do the test, towards the end of the class, you can go to tools and prepare handhelds, and then you do exit and you send that again. And instead of going calculator to calculator, which we know is quite time consuming, we can get that pretty quickly. If I go back to the main features on TI Nspire for IB exams, we know we use one variable statistics, we can do regression lines, polyroot finder. It all works if we have those proper settings in press to test, numerical solve system of linear equations, probability distributions, complex number tools, calculus, all those features we showed today will work. Tangent line does work in press to test, graphs with trace analyze graph. Now, geometry features are disabled as well as coordinates and equations. You can't get those, vectors, 3D implicit, and conics. If we look at relation, which is the new feature in graph and entry, it is highlighted in press to test, but it will not allow to draw x, f1 in y, which you can do in your class activities, or inverse functions. So if I go back to my screen and I will get a new graph. And if I go to menu and I do graph entry relation, so what you can do, and that will actually work, if I go y is, let's say, greater than square root x minus 1, it does shade the region. This function works. Anything with starting with y and inequalities does work. You can't enter x in press to test, but of course for class activities you could do that. So if I now enter, let's say y equals, no, not equals, I will do so, less equal to x plus 2, then I have this other region. Notice that this line is dotted because I had greater, this line is continuous because it is less, and you could get the relation, the region, of course the overlapping region here. What is possible for class activities if we are in this new entry, let's say if, actually I start with the normal function, so let's say I do the simple e to x minus 1 graph, and now if I change graph entry to relation, and now I say x equals f1 in y, it will graph you the inverse function. However, this feature will not work in press to test, but in class activities you can still do lots of those features and you can graph other relations. But again, it is more for teaching and pedagogical things in your classroom than in press to test mode, but it's good to realize what's happening and what's possible and what's not. So thank you very much for your attention, and all those files, as Rodney said, will be available for you to play and try. So now
Thank you, Bozenna. You just demonstrated some wonderful new features of the operating system 4.2. So for the audience, it'd be great if you update your software or in your handhelds. So wrapping up, so thank you to Pam and Bozenna. So if you look at the Education TI Australia website, and you'll find in the middle of the website, you'll see the webinars icon. If you click into there, so if you're looking for any recorded webinars and upcoming webinars, so at the moment we've just seen the webinar tonight from Pam and Bozenna here. So the new program is just about to be put on the website, so watch the space and look out for it and register for the new webinars that are coming up. And also you've got the on-demand tab there as well, and you'll see as you go through many recorded webinars and the associated documents, the TNS files and PDFs. As you go through, you can see there over the last few years there's many webinars. So at the end of this webinar, please complete the survey. It's very important to give feedback to the hosts and Texas Instruments Australia. Sign up for the newsletter. And don't forget to keep an eye out for the email that has your link for the certificate of your participation and viewing. Take care, and we look forward to your participation in future webinars. Thank you, Pam. Thank you, Bozenna.
It's been a pleasure, Rodney.
thank you very much.
Bye for now.